Good morning, everyone. Thank you for showing up for your learning on this beautiful Monday morning. Very happy to be joining you once again today to talk about what is a function. Now, I love this course. As you know, I love functions and working with them, and you've been discussing a couple functions already. One was how your money was going to grow if you were going to be cryogenically frozen and have it kind of double every year. That doesn't double, but they're going to add how much you invest each year, 100% simple interest. Okay, that creates a function. Maybe some of you recognize that would create a line, something that you've been studying since grade 9. And then your other option in this challenge problem was to invest it with compound interest, which is going to create an exponential growth curve. Those are also functions. So answers to these questions and many more coming your way in 3, 2, here we go. So what is a function? Well, it's a special kind of relation. Now, when you go to your handout, you're going to notice that you have these definitions on here. So they're important. So let's take a look at these definitions. So we want to know, what is a relation? What is a function? Relations are just relationships between x and y. All right, they're relationships between two numbers. The temperature outside and the amount of ice cream that is sold would be a relationship. When it's very, very cold outside, we don't sell much ice cream. When it's very warm, you'll sell more ice cream. So there's a relationship between temperature, which we'd probably put on our x-axis, and amount of ice cream sold, which we'd put on our y-axis. Yeah, or number of hours traveled and how far you've gone. We'd have number of hours traveled along our x, how far you've gone on our y. There's a relationship between these things. So now relations, just any identified pattern is a relation. Functions are special. Why, Mr. Jennings? Okay, for any one x value, there can be only one y value. So what that means is each input has to be unique. There's one output that each input will give you. So this is why it's useful to think of functions like vending machines. So here's our vending machine. All right, and I'm showing you a picture not because I think you're unfamiliar with the concept of a vending machine, just because it's going to help me talk about this metaphor. A function, it's like a vending machine. Okay, we have an input that we're going to put here. It's a special code that the customer will enter. That's our input. Remember, inputs are x values. Okay, so we're going to input something. For any one input, the thing that comes out should always be the same. Okay, if I push H35, I should get this pack of M&Ms, okay, because that's under H35. M&Ms come out, okay? If the next time I go to that machine looking for M&Ms, I push in H35 and chips come out, I'll be angry. So that would be a strange vending machine. That would not be a function. Any one input should have the same output. Now, that does not mean that different inputs couldn't give you the same output. Okay, let's say we had chips here and the same kind of chips there. Okay, some vending machines, maybe they sell a lot of these yellow chips, so they have two rungs full of the same chips. I could have two different inputs that would give me the same output. That's okay, that can still be a function. But anyway, a function is like a mathematical machine. It takes your input and it transforms it into something else. It transforms it into an output. So it's very much like a vending machine. All right, so let's keep going. So functions, yeah, they're the special ones. Every function is therefore a relation, but not all relations are functions. Every Porsche is a car, but not every car is a Porsche. Oh, let's keep going. So we should be able to look at functions that are represented as tables of values or ordered pairs, mapping diagrams, equations, and graphs. All right, and mapping diagrams, we haven't really looked at these very much, and to be honest, we're not going to look at them very much, but they show up today, and you want to recognize what a mapping diagram is. But the other three we're very familiar with: tables of values, just points and lists of points, lists of ordered pairs, equations, and graphs. Okay, those are the three like bread and butter styles of showing information in math. Now let's keep going. Here's some examples of some functions that you're going to see in other fields of study. You're going to see these in university, you're going to see these in other subjects, and you're going to see them from your life. So this is a function that a pharmacist or a nurse or a doctor would have to be very familiar with. This is the curve that represents the concentration of a drug inside someone's body. So this is important to know. You don't want to overdose someone. You take the drug and it's absorbed in the probably the duodenum. Maybe some of it is absorbed in the stomach, or it could be absorbed under the tongue. But in any case, comes into the bloodstream and it reaches its maximum concentration. And it's in here that the liver starts kicking in and metabolizing that drug. That's a slower process, and you can see that the liver is going to metabolize that drug and bring that down, 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 down. So this represents a relationship between time and concentration of a drug inside someone's body. So it's relating those two things. It's clearly a relation. And we can see that there's only one output for any given input. For any given time, we only get one output on this thing. So it is a function. Okay. Yeah, so that's one example, a cool example of a cool function. Let's take a look at another one. Here is something that talks about compound interest. This is a line. This is interest with no compounding. That's like the simple interest that we talked about in the cryogenic freezing, right? So it makes a line. Here is a compound interest, which is actually exponential. It grows faster the bigger it gets. All right. So yeah, also functions. Okay, these relate amount of time to how much money you got. All right. So time is money. You've heard this before. Here's a picture showing you time is money. All right, let's carry on. And here's another one, rockets. Okay, this is how they accelerate. The first stage of the rocket goes, and the acceleration reaches a maximum, and then that stage of rocket falls off. At which point another rocket kicks on, and it's a slower acceleration, and it grows, and then it drops off, and quickly is picked up by another rocket section, and then finally the rocket is finished its acceleration. So this measures g level or acceleration versus time in seconds down here. So this is from like the Apollo space rockets. Okay, so it's pretty cool. You're going to study that in physics, or if you want to say I study rocket science at school today, now you can say that. All right, here's in music, just like some really simple functions, sine wave functions that represent some really simple sounds. Okay, you know that sound is a wave, like a sound wave. So this is a picture of a sound wave, and it's also a function. As time goes along, the air oscillates. The air has a wave, and for any input time, the loudness of that wave, there's only one value there for any one time. So it's a function. This relates time to loudness. All right. And then this is higher pitch, this is lower pitch, etc. And that has to do with the period. And we'll study this when we look at trigonometric functions. Okay. Now, I wanted to quickly create a function with you all. So humor me as we go to Desmos. And I want you to see how to input a table of values into Desmos, because I don't think many people know how to do this. You go over here, you click Add Item, click on Table. Okay, and then it will open up a table for you to input. So what we're going to input here as X is number of hours studied per week. All right. And so last week the student said, 20 is a good upper limit, or like 21 hours of study. So let's say we have Boris, and Boris studies 20 hours a week. And then in the Y's, we're going to explore the relationship between hours studied and marks. So Boris, he studies 20 hours a week, and he got a 95 last year. Oh, good for you, Boris. And then there's another student, Harjinder. Harjinder also studied 20 hours. He didn't do quite as well as Boris, but he did pretty well, as you would expect. He studies consistently 20 hours a week. So he got a 91. All right. And then there was Steve, and Steve studied 10 hours. And Steve did very well, and Steve got an 87. All right. And then there was also Lacey, and Lacey studied for 10 hours. And anyway, you get the idea. Okay, so this is how you put in a table. So I'm going to do that. All right, so I've got how many students here? 8 students, okay? And they study a varying amount. We have a couple students that study 20 hours each. There's a couple students that study 10, a couple students that study 5 hours a week, and a couple students that study 0. As you could have guessed, the ones that study 0 tend to do a little worse than the ones that study quite a lot. But there's still some variation there for the individuals and just blind luck. So now you'll say, well, I can't see any of your points on the graph. That's what this button down here is for. So you click that and whoop, there's all my points, okay? Now, what I have here is a relationship between number of hours studied and average marks that those students got. Is this a function? No, it's not. And why? Because I have multiple outputs for the same input. You see, if I have 0 here, I had two students that reported they studied 0 hours. One said he got an 80, one said he got a 55. Okay, I had 2 students that studied 20 hours a week, and one got a 95 and one got a 91. All right. And so this is not a function. Okay, I can't use this to say if someone studied 10 hours, what mark did they get? Because they get 2 different answers. This is not a function. But if I took an average of all of this, and what I can do is put a line of best fit through here. And the way I type that is I write y1. That corresponds to all of these values down here. I want you to pay attention to what I'm doing. You're not doing it today, but we'll do it when we get the Chromebooks later this week. Y1 tilde. So tilde is like kind of equal to, is what tilde means. It's like an equal sign, but it means approximately. Y1 tilde m some slope times x1, okay, plus some value b. Okay, there's my line of best fit. Now, I could use this line of best fit to have someone say, well, I study 15 hours a week. What mark do you think I have about? And I would say, well, you probably have a mark somewhere around like 87. Okay, that's what this line would predict. This line is a function. It's a function of number of hours studied per week compared to the average mark that you would expect someone who studies that much to achieve. There can only be one number for the average, so that's why that is a function. But this set of points is not a function because it shows merely a relationship between hours studied and mark. Because I get multiple outputs for a single input, with the points, it's a relation. It's not a function. The line, on the other hand, is a function. Okay, so that I hope that inspires you to study more, and also that it helps illustrate what this idea is: a relation versus a function. Let's carry on. So when we're looking at tables of values or ordered pairs, okay, each x value has to have a unique y value for that to be a function. In other words, no x value may repeat itself within a table of values or a list of ordered pairs given by x, y's. So now would be a good time on your handout to say, well, how am I going to recognize it from a table of values? And I might circle that, and I might say no x value repeats. They're all there. There's only one entry at any input. Okay, so that's how I would recognize it from a table of values or a set of pairs. Now let's take a look at a mapping diagram. When are we going to see these, and what is that going to look like? So here's a few sets of points. These first two are functions, and the reason is because we have -2, -1, and 2 as our x values. None of the x values are repeating. Down here, on the other hand, if I said, well, my input is 1, what output am I going to get for this function? Well, this one is input of 1, output 2. But then I also have input of 1 and output of 4. So that's not a function. Okay? Because I have an x value repeated. I don't know what the output is at that point. It could be one or the other. So it's not a function. This one here says if you input -1, it will output 0. If you input 0, it will output -3, and so on and so on. All of the inputs are unique. Okay, so if we go back to this table of values, we knew this was not a function because we have these x values are repeating. That creates the 2 points per input, which means that's not a function. This, however, this is. We're going to see equations in just a moment. All right. Now let's take a look at mapping diagrams. So mapping diagrams are just ways of showing how do the inputs get transformed into the outputs as they go through this function machine. Or, the inputs into the vending machine, how does that get transformed into the outputs? So mapping diagrams are visual representations of input values of a relation and the corresponding output values of that relation. So mapping diagrams represents a function when no x value corresponds to more than one y value. So we probably want to write that down there. No x value corresponds to more than one output or y value. Yeah. So we should only have one output per input. All right. Now, we carry on. So, it's over here. I need to move myself there. Okay. So here's our examples of mapping diagrams. This is what they look like. And this mapping diagram indicates that if you have an input of 3, the output will be 10. Here we see two inputs that are different, but they create the same output. That's no problem. That can still be a function. Over here, on the other hand, this input of -1 seems to produce either 3 or 4, therefore not a function. Right. Now, when we're looking at graphs, we want to do something called the vertical line test. Right? The vertical line test means, so vertical, just a reminder, it means up and down. If you are dancing horizontally, you are not dancing, probably, unless you are breakdancing or doing something I don't understand. Most dancing happens vertically. Okay, so just remember vertical dancing. So a vertical line test means if I look at a function and I can draw a vertical line across that function, and that vertical line only ever touches the function at one point, then it's a function and not a relation. So, for example, I can take a line, and if I draw if I imagine some vertical line that I can draw through here, that only will ever touch at one point. Doesn't matter where I draw it. Okay. Now this is a parabola. It's a good example. It's not the horizontal line test. I can draw horizontal lines and hit 2 points. No problem. It's still a function. It's the vertical lines. They should touch at only 1 point. On the other hand, over here, I draw a line through there. It hits at 2 points. So your equation of a circle in the xy plane, that's not a function. It is a relation between x and y. It's not a function. Okay, so that's how you would determine if these graphs were functions or not. So let's clear that and do that and write a little note. So on a graph, we use the vertical line test. And if I were you, I would be drawing some pictures down here in this space over here to remind me of these things. So this would be a good spot to have a little xy plane. So I can draw my xy plane, and I can draw a function like this. And I could say passes vertical line test. Function. Because that's a function. If I put any vertical line through there, it touches at only 1 point. Right? And then I might have a picture of a circle there, not a function. Fails the vertical line test. 2 points. Okay, so that's particularly useful. You all want to remember that. And then in equations, recognizing functions from equations is very important. So let's take a look at that, and then I'm just about ready to say, get at it, everybody, get at it. So let's go here. Move me. I keep on putting myself over my buttons. All right, so we know that's not a function, fails the vertical line test. What about equations? Well, a linear equation given by y equals mx plus b, and we saw some of those today when we looked at a line that might predict your marks, or a line that would predict how much money you would have in different years. Y equals mx plus b. There's one x value for every y value. Right? Quadratic relations given by y equals ax squared plus bx plus c. There could be as many as 2x values for every y value. And so when you look at the power that x is raised to, you see this pattern? That if I have like ax squared, then I can have 2x values for every y value. As that power goes up and up and up, that's how many potential values or potential solutions I can have at one point. Now, in these equations, these y variables are always to the power of 1. Okay? That tells me that there's only one y value for a given x value, because y is to the power 1. So when you have the equation of a circle, for example, like here, y squared, we can say, well, that's probably not a function because I'm squaring my y value. It's being raised to the power of 2. That can lead to things that have multiple outputs for the same input, and we wouldn't want that if we were calling it a function. Okay? But over here, y is equal to, and then x is on the bottom. This is a function because y is not being raised to the power 2. Same thing here, y equals x to the 3 minus 2x squared plus 4. I mean, that's a function. It's going to pass the vertical line test. I'll show you. So this is what that function looks like. Okay, x to the 3 minus 2x squared plus 4. Notice it looks like curvy, like a parabola, but it has two bends in it. This is why if I draw some like horizontal lines, if I say, well, what is x if y is 3? And here's the line y is equal to 3. I could have graphed it. That would have been better. I should have just graphed it. But anyway, like y equals 3. Notice that hits at 3 points. 1, 2, 3. All right. So there's 3 places where y is equal to 3. So that's why can I have 3 different solutions there? Because this is x to the 3. Okay. When we add x squareds, those can have 2 solutions because it's to the 2. Okay. To the 3, we can have as many as 3 solutions, and so on and so on. But all of these have y to the 0 power. Okay, y to the power 1. That means there's only one possible output for any one of these. So if I go over here, clear the screen. If I look at any vertical line, like I can draw lots of vertical lines over here with like, x is equal to. If I say x is equal to 3, or x is equal to 2, for example, I'll draw a vertical line there. It hits both parabolas and this equation at only 1 point. If I make x is equal to b and I put that on as a slider, give me a slider. Anyway, some reason it's not giving me a slider, but it would only touch at 1 point. The vertical line test would be passed for both of these functions. So they're functions. They pass the vertical line test. All right. This not a function because we're raising y squared. So now it's a good time to go and fill in the last bit of our note for today. So for equations, we want to say y should not be raised to a power other than 1, i.e. y equals blah, 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 blah. Those will be functions. All right, so let's write some down. X squared plus y squared equals 9. Y squared, therefore not a function. And we looked at y is equal to x cubed minus 4x squared plus 4. That is a function. And so now you know how to recognize functions that are tables of values, graphs, or equations. Now, let's go back to that challenge problem that we had earlier today that you discussed, I hope, and we'll talk about that. So we start with like y equals $1,000. You had $1,000 to invest, and you were going to get that returned to you or doubled every year. They were going to add $1,000 per year for you. That's 100% simple interest. You were going to be frozen, until the year 3021. So we're interested in X values that go as big as 1000, right? And we expect you to have a lot of money by then. Let's say Y values of up to, like, I don't know, let's say 2 million. There it is. Okay. So now this is a function, right? And this function would indicate how much money you would have at different years. So this is 500 years in the future. Your $1,000 would have grown to $500,000. This is 1,000 years in the future. This is how much money you would have had. You would have $1,000,000. It's pretty cool, right? You take $1,000 today, just get someone to give you 100% simple interest, and you can grow that money to $1,000,000 in 1,000 years. All right, so that's that option. Then we also talked about, what if they gave you, instead of 100% simple, 1% compound interest? And I asked you to decide, which would you rather have? Okay. So in this case, we actually put in y is equal to 1,000, and then we're going to multiply that by 1.01. Okay, that's 1%. Okay, that would be 1% interest. That would return $10 after 1 year. This one returns 1,000. So I'm wondering how many of you are saying, yeah, I'd still go with that one. They're giving me $1,000 a year. This one, they give me $10 in the first year. That's nowhere close. It can't possibly be as good. But the thing with compound interest is, now we use the x as an exponent. Now we raise this to the power x. What? Look at that. In the beginning, it's hardly growing. This is a relationship between time and how much money you have. Okay, it's hardly growing, and then suddenly its growth starts to accelerate and go faster than this one's growth. And it crosses at the year 650 years in the future, okay? And at that point, you're going to have more money with the compound interest, even though it's only 1%. How much more? That goes up to about 20 million. Okay. So even though this is only 1% interest, like every year I just multiply by another 1%. If I put this into 1,000, I'm just multiplying by this 1,000 times. And that 1% adds up so much. Compound interest, very powerful. So we're going to be studying those types of functions, exponential functions, later on in the course. That's very exciting because you're young, you've got a lot of years, and you can get your money to do some exciting things where it just will bend and just climb skyward just in time for your retirement. So it's a very important function that's going to have a big effect on your lives. And I hope that helps you get excited about your homework for today, and to certainly email me any of your questions. Find me with your questions, and I'll see you in a little bit for a lesson on domain and range. Bye for now, everyone.